Welcome to EDU World Space.
Alright guys, we're doing problem 84 of chapter 9 in Chemistry Central Science. So the iodine bromide molecule, IBr, is an interhalogen compound. Assume that the molecular orbitals of IBr are analogous to the homonuclear diatomic molecule F2. Which valence atomic orbitals of I and Br are used to construct the molecular orbitals of I2, of IBr, or not I2, my apologies. So we'll use the simple atomic orbitals that are available to us. So you can see that the electronic structure that's right here of iodine and bromine. So that means we're going to be, so when we fill up the molecular orbitals, we'll use the 4s and 4p orbitals from bromine, and we use the 5s and 5p orbitals from iodine. But in terms of the molecular orbital diagram, we're going to be focusing more on the electrons in the p orbital because those are mainly what's going to be involved for our bond. Those are what's really going to be involved in the in our bonding process. So part B, what's the bond order of the IBr molecule? And you can see that here. So we have our non-bonding orbitals, which are here and here. And then we have our bonding orbitals and our non-bonding orbitals. Sorry, our bonding and anti-bonding orbitals. So we fill our electrons in our sigma and both our pi orbitals, and then we filled up electrons and we filled up both of the anti-pi orbitals. So when we fill electrons in our anti-pi orbitals, that's going to cause our bonds to weaken. So that means that these electrons in our anti-pi orbitals, those are effectively going to cancel out the strength of bonding from our pi bonds. So we're only going to have sigma bonds. So we're going to have of one single bond. So our bond order, that's going to be equal to 1. Now see. Now if you look at this problem in your textbook, you're going to see the valence molecular orbitals of IBr. Those are sketched. So let me see if I can draw that. So So they want to why are the atomic orbital contributions into this MO or this molecular orbital different in size? Yes. So the atomic orbital is different sizes because the orbitals of iodine are a higher energy level because they're lower in the periodic table. The iodine is lower than the bromine and is represented by orbitals in the 5th energy level. So remember, when you go down the periodic table, your atomic radius is going to increase. So conversely, you can think of that as the size of your electron cloud. That's going to increase as well. So because iodine has a higher atomic radius and a larger electron cloud when it's forming its orbitals, that's going to cause the contribution of iodine to be greater than bromine. So part D, what is the label for the M molecular orbital sketch below? So these orbitals are sigma bonding and anti-bonding orbitals that are formed by the sigma bond. Because remember, we only we only have this is only we only have a sigma bond in our molecule. We only have a sigma bond in our molecule because the electrons in the anti-pi orbitals are canceling out the double and triple bonds we would have formed due to the presence of electrons in our pi orbital. So these are only so these orbitals are just due to our sigma orbital, which is formed by the sigma bond. So these are our sigma bonding and anti-bonding orbitals. And these are formed by the 4p and 5p orbitals. In iodine's case, it's 5p orbital. In bromine's case, it's 4p orbital. Because we're only using the p electrons to form our bond here. So for part E, for the IBR molecule, how many electrons occupy the molecular orbital sketched below? Yes. And so we can see that at no electrons occupy the molecular orbital of our no electrons occupy the molecular orbitals of IBR. You can see that in the picture. You do not see in that valence molecular orbital of IBR, you don't see any overlap between the iodine orbital and the bromine orbital, so there is no electrons occupying in that. So there's no electrons occupying that molecular orbital. So because this would be us because we don't see any kind of overlap here. So there's no interaction.